So, welcome back. Last video we have seen an example of piecewise continuous function, in fact piecewise smooth function, piecewise differentiable function for which we have derived a Fourier series. We promised to give you what is called Gibbs phenomena for a Fourier series at discontinuous points. That is actually it is technical only, it's a technical point of view only you have to explain. So, there is nothing more insight of Fourier series, on Fourier series when you discuss about the Gibbs phenomena. So, we will see what this Gibbs phenomena through this example. So, I will just briefly explain what it is. When you have a Fourier series like this and you try to fix this, you take only finitely many terms. For example, n is from minus k to k 1 by pi times n is not equal to 0, and this is your Fourier series, and you try to compute this Fourier series. You try to plot this thing for k let us say 10 terms, 20 terms and bigger terms. So, fix some big n, k equal to big N, you fix this and you try to plot. So, eventually we know that this converges to this, we know that this converges to f x once you fix x as k goes to infinity. So, as k bigger and bigger, this converges to f x. What is actually happening once you fix this k, which is some big number n, what you see at the discontinuous point 0 is a discontinuous point, and what happens here is that see this is actually converges, you are actually converges, eventually it converges to here at this value, this is at minus half, this converges. As it approaches the discontinuous point, you will see some fluctuations, and you see that there is a big fluctuation here, and then it goes to 0, and then it goes to, so do the same thing. So, there is a fluctuation up there, and then it goes like that. This is how it converges. So, what happens at the point of discontinuity 0, and what you see is that there is a jump here, there is a value actually as at x equal to 0. At x equal to 0, you see that there is a overshoot of the overshoot value of this finite sum. This finite sum, if you call it Sn of x, Sk of x, so overshooting value as x goes to 0 plus side, if you see that there is a overshoot here, there is also overshoot here. Okay. If you observe, if you just plot it, you will see that. So, maybe I will just show you eventually sometime later in Mathematica, I will show you how the plotting of this function, when you take finitely many sum of a Fourier series at discontinuous points, how it will be looking like this. So, you will see that there is a overshoot, that means the extra value here. So, this value is more here, the value at this point, at the end point, the value is more. What happens actually as k goes to infinity, this outside this right side of 0, whatever fluctuations you see, they fizzle out, there will not be any fluctuation, they eventually converge to the constant half, and what you end up, but this constant will remain be there. So, this fluctuation at the 0 at extreme point is always be there. So, that extra error is always observed to be is shown to be observed, whatever may be the n value you fixed. Eventually for every x positive value it converges to half here, as converges to 0 negative side this goes to minus half. Here also the negative side here it just converges to the value minus half, but here and eventually here there is a overshoot always. Here also you will see that here also you will see the overshoot value. There is a overshoot value here also. So, that error happens to be always some percentage, let us say some 9% of some percentage of error around x equal to 0, always there. So, that is called Gibbs phenomena. We will try to explain this in the next video. Thank you very much. Welcome back. We will try to explain Gibbs phenomena through an example that I have worked out in the last video, and we start with the example. So, that example what we had is fx is piecewise continuous function, in fact piecewise smooth function, 0 less than x less than L by 2 and minus half when you have minus L by 2 x less than 0. So, it looks like you have a positive side and negative side minus half and positive side is half. At 0 you have a discontinuous point, this is from minus L by 2 and this is from L by 2. Such a function, as we have already explained, so normal signal what with elementary functions is always piecewise a differentiable function. So, this is piecewise differentiable function, that means it has a derivative which is continuous, which is differentiable except at finitely many points. Here also it is continuous at finitely many points, it is differentiable. So, this derivative 0 is here, 0 here, at 0 it is not differentiable. So, it is piecewise a differentiable function. Even if you do one more derivative f double dash, that is also 0. So, that is still at 0 it is not defined, if f dash is not defined, f double dash is also not defined, so on so on. So, you can easily see that all derivatives f is many times differentiable, but it is piecewise a differentiable function. So, you can say that f is piecewise differentiable, that means f dash exists as a piecewise continuous function. F double dash is also similar thing, f double dash exists except at finitely many points, as at those points it has a jump, finite jump. Okay. So, we have considered the simple example and we constructed the Fourier series. So, what we had is this Fourier series this is what we get the Fourier series. So, I take the not the final form, what I get is I go from minus infinity to infinity, n is odd and this is what you have, and this is Cn's. So, we will just try to pick up from what exactly that form. So, this is the form we are interested. So, this is the form we are interested, minus I by pi n e power I n. So, you write like this, minus I by pi n, this is my Cn, and e power I n omega naught x. So, this is the Fourier series that is valid between x belongs to minus L by 2 to 0 union 0 to L by 2. We have seen this. We will try to manipulate this and eventually we will show that this phenomena, of Gibbs phenomena around the discontinuous point, we will just show for this example. So, what we do is we will try to write this from n is from 1 to infinity and n is odd. So, what you have is minus I by pi times n is odd, n is running from 1 to infinity. So, you have n is odd. So, it starts with 1, 3, 5 and so on. So, it should be 2n minus 1. So, when you put n equal to 1, it is 1, 3, 5 and so on. So, this is what you have, and here also I 2n minus 1 w naught x. So, I have written n is from 1 to infinity, positive side all n odds I considered, and this is what is the result. So, what is the next part? Other part is n is from minus again 1 to infinity, and here minus I divided by pi times n is odd and negative odd, that is negative odd you can consider minus of 2n minus 1. When n is from 1 to infinity, and you see that it is going to be minus 1, minus 3, minus 5 and so on, that is exactly what you want. So, n is from 1 to infinity, if I replace pi minus 2n minus 1 minus plus 2n minus 1. So, this is what happens to when I replace n by minus 2n minus 1. So, minus plus I divide by pi times this e power minus I 2n minus 1 w naught x. So, these are same. So, these are the two sums, we can combine it, and what you get is n is from 1 to infinity. So, you can combine this and you write minus I divided by pi times 2n minus 1 and this sum is 2 times this difference. So, this is basically because I have taken negative outside, this difference is 2I times sine 2n minus 1 w naught x, when I add this one and this one together. And this is equal to I square minus plus. So, what you get is n is from 1 to infinity 2 divided by pi times 2n minus 1 sine 2n minus 1 w naught x. Okay. So, this is exactly your f of x, your function, given function x belongs to minus L by 2 to 0 union 0 to L by 2. This is always true function value. At discontinuous point, we have already seen that if f is a piecewise differentiable function, and we have seen that the Fourier series, actually this Fourier series converges to the average value of the function at a discontinuous point. So, what we try to do from here is that we will just see, if you actually see, if you consider in this series, if I consider only finitely many terms. Okay. So, if I consider finitely many terms of this series, let Sn be, Sn of x be simply, let us take Sk, let us take k, n is from 1 to k. If I take k terms in this series, what you get is 2 divided by pi times 2n minus 1 sine 2n minus 1 times w naught x. This is for full sine function of this thing. This is the whole thing, sine of the whole thing. So, if I consider this, if I plot this, you will have, because these are composition of sine functions, you will see that it will have oscillatory. If you plot it, it looks like oscillatory function. So, if you do so when you do this around 0, the plotting is like this. Eventually, as k goes to infinity, this Sk of x converges to half of the value. So, this is minus half and this is plus half. By the convergence of the Fourier series, this plus this and divide by 2, that is what we have, right. So, that is 0. So, we know that it is going to be 0. Okay. At 0, around at 0, okay. At 0 it is going to 0. If I choose, what happens in the Gibbs phenomenon, what we have is, what happens is that around this point you will have, it will go like this, and there is a phenomenon like this, there is a, eventually it fizzles out. As k goes to infinity, these small oscillations will vanish, but this bigger one, whatever may be the small quantity, that will remain. Similarly here, that is what is the Gibbs phenomenon. So, this exactly this around 0, negative side of 0 and positive side of 0, this peak at which this value. So, this peak is always will be there. So, that is exactly the overshoot value of the function. That is what we will say. We will see that that is the error, that is called Gibbs phenomenon. So, at what value this peak will happen? The first peak that eventually will be there, okay, as k goes to infinity. Otherwise, there are many peaks. This is another peak, this is small peak. These are local maximums. Similarly, these are local minimums. If when you have oscillations, this is local minimum and this is local minimum, this is and so on. So, among the first local minimums, right side and left side, first local minimum at which you have this peak happens. So, we will try to see that. To do that, as we know, if you want to find the local minimum and local maximum of a function f x, you need to find the derivative, make it equal to 0. So, the roots of this, those are roots of this function f dash of x equal to 0 will give the critical values. At those values, you will have local maximum or local minimas. Okay. So, we will consider exactly what those values around 0. First value will be, we will just take, we will find out what exactly those. For that we need a function derivative. So, Sk is this. So, we need Sk is basically as k goes to infinity, this is actually f x, this is the Fourier series. So, for this Fourier series we need derivative. So, we will just try to find what is f dash of x, because f dash of x exists. You see that given that f of x is a piecewise differentiable function and it has a Fourier series Cn e power I n omega naught x. This is what we have, minus infinity infinity. So, you have a Fourier series because f is piecewise differentiable function, and we have considered an example that it is a piecewise differentiable function. One is half and minus half and plus half, and because these are elementary function, constant function, it is also a derivative f dash of x is also piecewise smooth. If you consider f double dash, that is also piecewise continuous function. So, for that reason I will have f dash of x also will have a Fourier series, that let me call it some dn e power I n omega naught x, n is from minus infinity to infinity. Okay. So, what are these dn's? Dn's are basically Fourier coefficients, that is from 1 by L minus L by 2 to L by 2, what for this function, a derivative function, that is f dash of x e power minus I n omega naught x dx. Now, if you simply do this if you do this integration by parts here, what you get is f x e power minus I n omega naught x for this 1 by L, and you substitute the limits and you have a minus 1 by L integral minus L by 2 to L by 2 f x. Now, you differentiate this function. So, you get I n, so that comes out, minus I n comes out, that becomes plus I n omega naught f x e power minus I n omega naught x dx. So, this is exactly our Cn. So, what happens to this one? This is this becomes at phi f at L by 2 and f at minus L by 2, and this becomes simply, if you calculate, this contribution will be 0. We will see what it is, f at L2 L by 2 and then e power minus I n, w naught is 2 pi by L into L by 2. So, L by 2 goes, so I n pi, e power I n pi. Okay. So, you have simply e power I n pi minus f of minus L by 2 e power plus I n pi. So, this is what you have. Okay. So, at L by 2 and minus L by 2 is actually repeating. So, this is the value at minus L by 2. Okay. This is the minus L by 2, this is at here. So, this is the x axis, this is L by 2 and this is at minus L by 2. It is a repetitive here. So, because it is a periodic function, what you see is L by 2 minus L by 2 is same as plus L by 2, it is a periodic function. So, whatever repeats here it will go. So, that way, and this is simply cos n pi cos n pi. So, this together, so it is 0. So, this contribution is 0. So, I will remove now, and then what is the other, what remains is I n omega naught 1 by L, this integral is nothing but your Cn. So, dn is nothing but is this one. So, if you get you know that if it is, because f dash is a piecewise smooth function, piecewise differentiable function, implies it has a Fourier series like this. If you calculate its Fourier series, and that is exactly in terms of Cn, that is nothing but n is from minus infinity to infinity, dn is now I n. So, I comes out I omega naught and then you have n Cn e power I n omega naught x. So, this is your Fourier series and that converges to f dash of x, wherever f dash is continuous. Otherwise, it converges to the average value of the f dash at those two values. Okay. So, this is well known, this is how we show. So we can actually calculate. So because we have considered such a simple example with elementary functions, whatever may be the elementary functions you consider, whatever may be the function f, piecewise continuous function involving elementary functions, is always piecewise smooth. That means it is piecewise differentiable function, and it is also piecewise twice differentiable, piecewise thrice differentiable, and so on. Okay. For that reason you can get this Fourier series for the derivative. So this f dash of x is now, so now your f dash x is this given function, and you have already this Fourier series, and then if you actually do this f dash, and what you see you can see that this is exactly, this is actually, if you observe, this is simply differentiate this term by term. If you differentiate term by term, I n omega naught. So actually given function f, this Fourier series, if you differentiate both sides, that is exactly what you got. Okay. So that way I'll just derive it here. So in that sense, this function, given function, this given function which is that given piecewise function in our example, we can simply differentiate both sides. Okay. I consider f dash f x, that is now the Fourier series I can simply differentiate term by term. So n is from 1 to infinity 2 divided by pi times 2n minus 1, and this becomes cos. Okay. So cos, and you have a 2n minus 1 omega naught into w naught into cos, this is cos 2n minus 1 w naught x. This is what is the Fourier series now. Its derivative Fourier series is this. Derivative of the function for which the Fourier series is has become this. This gets cancelled. Omega naught is 2 pi by L, and you have 4, pi goes 4 by L, and you have n is from 1 to infinity. Simply have a cosine cos 2n minus 1 w naught of x. Now you can rewrite this cosine cos. So I use cos 2n minus 1 w naught x into sin w naught x, 2 times of this. This is equal to sin sum plus sin difference is 2 sin sum plus 2 sin A cos B is sin sum sin A plus B plus sin A minus B. That is what I am going to use here. So if I use this what is the sin sum? Sin sum is sin 2n. If I add this 2n w naught, so 2n w naught x minus, because this is starting with cos, and that makes sin sum plus sin difference. Sin sum, sin difference will be minus 2. So this is sin sum. So let us say this is sin sum. So sin A cos B plus cos A sin B. So that, right. So that is this one plus or minus, when you add this goes. So what you have left with is a sin A is this is your B. Okay. So A minus B, so sin sum is this, sin difference is A minus B is sin A minus B is w naught x. So 1 minus plus 1, so that is 2 minus 2n into w naught x. That is what it is. Okay. So I will just remove this. So this is what you get. So if I use this, what you end up is f dash of x is equal to sigma n is from 1 to infinity 4 by L, let me write inside. Now this cos I will use this one here. So this right hand side divided by 2 sin omega naught x, 2 sin omega naught x, and this will be sin 2n omega naught x, and this I will take minus, you have a sin 2n minus 1. okay, 2n minus 1 w naught x. So, this is what it is. So, I replaced cos function which is here is by using this identity. Okay. So, once you have this, this is equal to, I will just rewrite this as a limit of some limit which is 2 divided by, so of course, you have a 2 goes 2 divided by L sin omega naught x, and you have this sum n is from 1 to infinity sin 2n omega naught x minus sin 2n minus 1 omega naught x. So, what is this one? Now, you look at this sum, you take partial sums here. If you take partial sums and limit k goes to infinity, this partial sum n is from 1 to k and whatever here. So, this is sin 2n omega naught x minus sin 2n minus 1 omega naught x. Okay. So, now because this is a partial sum, if you expand it, starts with 2 omega naught x minus sin 0 and then plus, so and then what is remaining? So, 2n minus 1, so that is sin n equal to 2 sin 4 w naught, and it is going to be sin, this gets cancelled. So, eventually what you end up is sin omega naught x limit k goes to infinity, this is simply sin 2n w naught x, so 2k w naught x. You write 2k, so basically 2k minus 2k minus 1, again you add when you put n equal to k minus 1. So, if you have a 2k minus 1 minus 2k minus 2, so this gets cancelled like this and end up finally an n equal to 1, this is simply sin 2 and then minus sin 0, 2 into 1 here 2 into 0 is 0, sin 0, that is 0, and this gets anyway cancelled. So, you end up only 2k term that is here. Okay. So, this is how I explain. So, you simply expand this finite sum, everything gets cancelled except the when n equal to k, the first term, this term only contribution will be there. So, this is exactly what you have as of now. So, this is my f dash of x, which is this is simply a limit k goes to infinity 2 divided by L times sin 2k omega naught x divided by sin omega naught x. This is my f dash of x. Now, I consider f dash of x is a Fourier series. Okay. F dash of x is actually your Fourier series. So, this is your f dash of x, your Fourier series. So, as partial sums, this is limit of a partial sums is actually your f dash of x. So, that is exact. So, that means this is your partial sums. So, Sn dash of Sk dash of x is nothing but 2 by L sin 2k omega naught x divided by sin omega naught x. Okay. What is your Sn? Sn of x is a partial sum of your Fourier series, actual Fourier series, that is this one. Okay. So, that is this is your partial sum, and you have its derivative is simply what you end up is this. So, this Sk dash is not exactly direct derivative of that Sk of x. This is a partial sums for f dash of x. Okay. So, this partial sums you have this one. So, if you differentiate, I think you will get the same. Sk dash of x is eventually end up as saying you may end up this one only. Okay. That will not bother. So, let me write what is that Sk sk of x, this is from sk of x, let me write sk of x, k is from 1 to n, 2 divided by k times, what is that, f s n k, 2 divided by pi n 2n minus 1 sine 2n minus 1 w naught x. That is exactly our Sn of sk of x. So, this is our derivative. So, if I make this sk dash of x is 0, sk dash of x equal to 0, what you end up is sine, sorry, yes, I think I have written wrongly. So, this is sine of this divided by sine of that. So, you have sine 2k w naught x divided by, so it has to be 0, if this has to be 0, implies this has to be 0. So, this means 2k w naught x is n pi, n is running from 0 1 to 3, any 0 1 to 3. Okay. At 0 you have seen, if you plot it a finite sum of Fourier series, you see that is eventually at you have a jump here. So, this will go from this to this, and at 0 it crosses like if you plot like this. So, 0 is inflection point that you can see by just differentiating one more time and see that it is still 0, okay, at k at n equal to 0. Okay. So, at 0, if I choose n equal to 0, k equal to 0, if n equal to 0, if n equal to, n is from 1 to 3 onwards, if n equal to 1, what is k? K is pi by, so what are the points you need? 2k, sorry. So, if n equal to 0, if n equal to 0, if I choose, then x equal to obviously 0. K is actually running from 1 to infinity. Okay. If n equal to 1 and so on. So, if n equal to 1, x equal to n pi by, or rather n equal to 1. So, you have pi divided by 2k divided by w naught. W naught is 2 pi by L. So, you have pi goes, you have L by 4k. So, this is the first value, and what happens n equal to 2? If n equal to 2, x will be equal to, of course, this can be even plus or minus, right. So, when I choose the plus side, this is the case. On the positive side, if I look at it, at x equal to 0 you have a critical value, at x equal to L by 4k you have another critical value. When I take n equal to 2 with positive sign, what I have is 2 pi by 2 w naught, 2 pi by L into k. So, this 2 goes, pi goes, this is L by 2k. So, this is bigger than this one, this is bigger than, this quantity is bigger than L by 4k. So, the first value on your right hand side when you have this one. So, the first peak, oscillatory peak value here will be around L by 2k. Okay. If you consider k values, k is running from, what is sk of x, and k is from 1 to right. So, sk, what is sk? So, you have a partial sum, sk is partial sum. If you have n is running from 1 to k, k terms if you choose, k terms, if k becomes bigger, this becomes close to 0, this goes to 0. So, it will be closer to 0. Otherwise, the first peak will be L by 2k, next one will be L by 4k, L by 4k is the first one, L by 2k is the second one, and so on. So, the first peak is here. Similarly, the negative side, when you choose n equal to minus 1, what you have is minus L by 2k, this peak, this lower peak, local minima, the value of x, that is minus L by actually, yeah, that is negative side. So, I have minus L by 4k. So, both plus or minus L by 4k, that implies at x equal to plus or minus L by 4k, we have local extreme points, extrema, okay, local extrema. If I increase, if k goes to infinity, so the first local maxima will be always be there, okay. As you increase k, there are other extremas. This is a local minima, local maxima, all those things will be there. They are all vanishing slowly because it has to converge to half. Here also it has to converge to minus half. So, but this first peak will always be at this one. As you fix your k, at these points you have local extrema, first local extrema. We have first local extrema on both sides of 0, that is this origin. So, we will just see at this point, at these values, what is the value of the function, okay. So, we will just try to calculate what is your Sk of L by 4k. We will just look at one side, other side is similar. So, this is running from n is from 1 to k, 2 divided by pi times 2n minus 1 and sine 2n minus 1 into omega naught x, that is omega naught is 2 pi by L, x is now L by 4k, right. So, 2 goes 2 times, L goes, and what you end up is simply n is from 1 to k, 2 divided by pi times 2n minus 1 sine of, this is the whole of sine. So, sine of 2n minus 1 pi by 2k. This I will try to rewrite like this. I will try to rewrite as a sum, finite sum, n is from 1 to k, sine function of sine 2n minus 1 pi by 2k divided by 2n minus 1 pi by 2k. So, I have to I have added what? So, this divided by this is already there 2k. So, 2k is 4k, I have to add 4k, or rather pi by 2 is already there, k is also there, yeah, this k is extra, and so k is extra. So, k goes up. So, if I have to do this, I have to simply divide with k, right. So, if this k goes, 2 goes up and pi into this is this 2 divided by pi times 2n minus 1 is same as this quantity. This is what exactly I rewrote. So, if I multiply 1 by pi, I multiply pi here. So, right. So, what is this one? This quantity is, this is now if I take the limit k goes to infinity, S k of L by 4k, this value, that means the value when you plot, what happens to the value if you take k goes to infinity, full Fourier series, as take more and more terms of the Fourier series and you sum it up and plot it, what happens is this fizzle, this oscillatory parts here and this side will be fizzled out, only we will have only this what happens here. So, we will have the Fourier series, the value of the function. We are now trying to calculate value of function here. We will see exactly the value, whether it is going to be half or it is going to be something always. We will see if it is what it is. So, this is going to be 1 by pi, this limit k goes to infinity, this sum n is from 1 to k, pi by k, okay, times sine 2n minus 1 pi by 2k divided by 2n minus 1 pi by 2k, okay. So, this is exactly this is a integral sum between 0 to pi, and you divide with k equal intervals with pi by n size, pi by k size. So, that I have pi by k times sine function. So, between any two intervals I simply have this is 1, 2, 3 and so on, right. So, this is pi by k, first one is pi by k, the second one is 2 pi by k and so on, finally k pi by k is pi. Okay. So, you have 2n minus 1 by 2 will always be in between. Okay. When n equal to 1, this is half. So, this is going you are going to be here. If n equal to 2, 3 and half. So, you are going to be here. So, exactly middle of that function value, middle is the middle of this interval. Okay. Middle of the sub interval. So, this is exactly equal to 1 by pi times this limit is this pi by k is the interval length and the function value at this middle point. Middle point is 2n minus 1 by 2 pi, okay, by 2 pi by k. So, what exactly the middle point? If this point is pi by k and this point is 2 pi by k, middle point is 3 by 2 pi by k. Okay, 2n minus 1 2 is 3 by 2 pi by k. So, exactly the middle value. Function value, what is the function? Sin x by x. So, you have this integral. So, this is the integral sum, that means it is going to be 1 by pi sin x by x dx. This integral sum is that. And if you calculate from the table of integrals, this value is actually 1 by pi times 1.852, which is the value is 0.589. So, as limit k goes to infinity. So, if k goes to infinity, what happens to this at this value L by 4k? It is eventually. So, this if you take bigger large values of k, this Fourier series, the more terms. So, partial sums of the Fourier series, you take more and more terms you choose, the value of the function here is not half, a little extra. Okay. If you take the function value as partial sum set minus L by 4 by k, what you have is minus of that is exactly, so you will get plus or minus 1. So, if you choose this one, and what you have is you will have only plus or minus half. So, that will give me plus or minus. So, you will have more one side is more here 0.58 something 589, here minus 0.589. So, what you are supposed to get always as k goes to infinity, you are ending up this one instead of 0.5 at this value L by 4k. As you increase bigger and bigger values k, sk at those peaks, you should get you expect it to converge to 0.5, instead you are actually converging to 0.8589 always, whatever may be the fixed k value. For any fixed big k value, you ending up this result. That means 0.089 is the error. Okay. So, this is approximately 9% error. Okay. So, this is called the Gibbs phenomena, whatever may be. So, this is simply a technical point of view. When you plot this Fourier series, whatever may be the number of terms you choose in the Fourier series, you always at discontinuous points, you always overshoot when you plot it. Okay. When you try to compute, you always overshoot the value of actual value of the function. So, this is called Gibbs phenomena. Okay. So, this is the Gibbs phenomena. So, normally, in the next video, we will try to give you properties of the Fourier transforms. So, basically what we have is you have a Fourier coefficients n, Cn's are 1 by L minus L by 2 to L by 2 fx, give this as a given signal e power minus I n omega naught x dx. So, these are your Fourier coefficients. If you call them, so it depends on n. So, if you call this, it depends on f and n. So, you try to call this as f cap of n. This is now function of n. So, if you call this, so you can say that this is the definition of your Fourier transform. Fourier transform of a periodic signal is defined as 1 by L minus L by 2 to L by 2 fx e power minus I n omega naught x dx. Then the inverse transform is fx, which you have is what you have is f cap n, that is your Cn's, n is from minus infinity infinity e power I n omega naught x. This is your Fourier series. This is the inverse transform, which is the Fourier series, okay, and this is your Fourier transform, some sense, okay, of a periodic signal. So, we will see what are some properties of we will see some properties of this Fourier transform. So, we will look into this Fourier transform properties, and some of when you say that this Fourier series converges uniformly, all these small results we will just prove in the next video, and these results will be useful when you do eventually Fourier transform on the full real line, okay. So, continuous Fourier transform, that is what we will see eventually, these properties and some of the results on delta function, that integral 0 to infinity delta function delta x dx. What is that value? That value is actually half of that. We will prove these small results. So, these remaining these small results, properties, and some of the results that will be useful later on delta function. We will see them, all of them, in the next video. Thank you very much.